First of all, this is going to be the lowest tech presentation you've seen. This is effectively on Notepad, and I'm just going to scroll up in Notepad. So I make no apologies. It's low tech. Deal with it. I'd like to show you what is a continually evolving idea for a merge operator. We can't even agree on the name at the moment, so I'll come on to that in a moment. But the motivation is, from a tool of thought point of view, that as this is an easy cell, we probably all accept that one of the sweet spots of array languages is that they let us think about our problem at the aggregate level, at the gross level, rather than having to dip down into the items that you do in scalar processing languages. And we know that gives us good tool of thought benefits. Similarly, the functional languages let us think about expressions for most of our work rather than having to deal with state. And there's a lot written in the functional programming literature about the benefits of trying to stay within expression thinking, just as there is in the APL literature about trying to think in the think at the array level. And we're in the fortunate position of being an array functional language, so that we can try to combine these. Currently, Dyalog lacks an expression for the triadic operation, which is that array, but with these items at those positions, which is an operation that we use quite a lot. And currently, we have to use a three-step procedure. And I apologise, despite many emails from Jason who said, you will be at this resolution. I did my notepad and spilled off the end, so I might have to scroll over a bit. So if we want to do that array but with these items at those positions, we have to do a three-step procedure, not an expression. First of all, we have to name the array, and these dots may be the result of an expression. So first of all, we have to name it. Then we have to mutate the array using indexed assignment, and then to use the resulting new value in further expressions, we have to use the name again to pass the value on to further expressions to the left. And wouldn't it be nice if we could embed some kind of mechanism within an expression, so that we didn't have to stop our expression thinking to do this. So effectively, what I'd like to do, the only moving parts in this are the x and y, the indices, the incoming expression on the right, the incoming array value on the right, the indices and the new values. So what I'd really like is to have these dots move down to here, the expression, and then something to do to replace the values and then continue. So I'd like to swap this for this, and this would help my tool of thought. Both J and K have such constructs, so this is not blue. The J and K languages have such constructs, so it's not pioneering. And while we're at it, it would be nice to replace modified indexed assignment, which again is a three-step process. In this case, we have we take the existing values at these positions, modify them with a function, and put them back. But again, it's a three-stage procedure. So perhaps we want something with three moving parts in it: the new values, the function, and the indices. Roger kindly pointed out to me that Ken has been, as with everything, Ken's been there before us, and in 1962 book he produces mesh and mask operations, and I believe these are good expressions. This is effectively meshing these two arrays together according to a Boolean selector. And mask is a similar thing where it's doing replacement. So the merge that we're discussing is quite akin to mask. There's a select function in the defense workspace. If you Google dialog space select, there's a kind of alternative way of addressing this problem, but that's aside from this this presentation. The first stumbling block was nomenclature. What do we call it? I personally like to try to find nouns for the names of functions. So I'd prefer to like square root and successor and floor and ceiling are nouns. So merge as a noun, the merge of two arrays is nice, except it gives the wrong impression because merge, if you think of streams of traffic merging, unless you're on the A33 going north of Basingstoke, both streams of cars make it through to the narrower lanes, whereas this is kind of pushing some of the cars into the ditch. The new cars push the old cars into the ditch. So merge is kind of okay. We can use it as a noun. I think J and K use amend, and maybe we'll use that to it. But I've a slight that sends me down a procedural way of thinking, so I have slight problems with that. Mask, Ken's mask, maybe, I don't know. And then in the bar on Monday night at around, I don't know, 10:30, it seemed a good idea to those of us left standing that the fuse or the fusion of these two arrays was a good, maybe was a good idea. So that seems to be the contender, the fusion of arrays. Okay, now trying to make a mechanism to merge arrays, I suggest that some design considerations are the most frequent cases should have the simplest expression. So if you're just doing very simple merge, or fusion, then that should generate a simplest expression. I try to avoid overloading an operator with too many cases. Try not to pack everything. So it's tempting to say we want to do this, but we want to do it at all. Possibly do merge arrays at all depths and all ranks, and the thing gets too complicated like that. But we don't also want to wind up with 6 different glyphs for doing it. Oh yes, and the other thing is, and as you will notice if you look to my right, a smile creeping after Mr. Huey's face, is that dialog has stranding, and so I have to parenthesize. If I have an array right argument, I have to parenthesize something to stop the right operand binding with the right argument. And I'd like to avoid parentheses. Okay, so my 2p, my 2 cents worth, is so fuse. We make a dyadic operator. Oh, one option is to make a special syntax for doing this, like selective specification is a special syntax. But let's try and stick with an operator. There's 2 things to do. There are 2 functions then. There's a selector to select the items from the array that we're going to be merging into. And then there's a modifier. So if I wanted to increment those values. So if we put the selector on the right and the modifier on the left, that reduces the parentheses. There's a lot of scope if the selector could either be a Boolean mask or it could be numeric indices. And for this, I'm experimenting with a Boolean mask here. Well, you can always translate from one to the other. And the selection operates on major cells along the leading axis, I suggest. So this is a model I've been playing with. How are we going to spell this? Well, I quite like the right arrow for this operator, and the plus points are it's quiet. It's not a noisy glyph. It's easy to type, and it is not confused with a branch arrow and suspension clear, because with a branch arrow and a suspension clear there is nothing to their left, whereas with this there will always be something to the left. It's a slight overloading, but right arrow seems to have dropped. You don't see many uses of it these days. So here's an example. So here's a spec of a program. It's a trivial program. I want to do a deal of an omega deck, which could be query commute omega, and then I want alternate items in this vector as zeros. So, for example, in quad IO1 with omega 5, the deal might produce 2, 3, 4, 1, 5, and then I want to wind up with zeros at alternate positions. And here's a little function. This is a bool returning function to give me a alternate zeros and ones depending on your origin. You start with the 0 or 1. Given a number 5, it'll return either 0, 1, 0, 1, 0 or 5. And or I could pre-compute a Boolean value. So what we have to do at the moment to do this is to name the expression, then do a Boolean compression, a Boolean selective assignment, and then dereference it. Whereas this would be replaced, this could be replaced with this, just this, which is a simpler expression, I contend. And because the selector is on the right, and I've made a mistake here. Oh no. This is okay. If I have an array here, I'll need to put a tack so that the B doesn't bind with a 5. Okay. If I use a function selector, then I'm good both ways. Okay, and then the incremented, and this says just replace with this value. If I want to replace with an incremented value, the plus sign, then it's the one increment of the selection from this array. And we can model this. I'm run out of time. We can model this with, you can't really see the model here, but it's an easy thing to model. And I'll make sure this model is in the defense workspaces. So what we want next is, I'm hoping for some discussion in Dyalog, or email me with suggestions, and I will try to explore possibilities. Thank you.
All right. 2 other new operators are proposed. I will demonstrate them through examples, but I encourage you to download the discussion papers and give us any feedback. The key operator, for example, benefited significantly from user feedback, and we're hoping the same will happen with these other proposed operators. The first one is the cut operator. It was first proposed by Ken Iverson in 1983 and carried forward in J. As you can see, there are separate cases. It's an operator with a function left operand and a numeric scalar right operand that impose the particular case. The symbol hasn't been decided yet, so I'll use CUT for the presentation and also in the discussion paper. The first 2 cases are the 1 cut and the -1 cut. So in the 1 cut, you have a leading fret, and then the function, the left operand function is applied to each cut. In this case, enclose each cut. And the fret is the slash, the leading cell. The term fret comes from the things on a guitar where you have those bumps separating the notes, I guess. And if you apply the tally function as the left operand, then you get the count of each cut. So tally function, leading fret is slash. So there's 8 cells in the first cut, 5 in the second, and 5 in the third, including the fret if it's the one cut. But if you want to exclude the fret, as happens sometimes, then you use the -1 cut. So here, and close each cut, excluding the fret. And the tally of each cut, excluding the fret. Okay, so tally, excluding, and then the fret is the leading slash. Frets can also be indicated by ones in a Boolean vector left argument to the derived function. So leading ones indicate the fret. So here I'm enclosing each fret. And here I'm applying summation to each cut. So the sum of 1, 2 is 3. The sum of 3, 4, 5 is 12. And the right argument can be an array of any rank. In this case, a 2-column matrix. So enclose each cut. So in each cut is a matrix, a 2-column matrix. Or apply summation to each cut. So you see 1 plus 3 is 4, 2 plus 4 is 6, and then 5, 7, 9 is 21, 6, 8, 10 is 24. So far it's similar to the partition function that's already in Dyalog. But one difference, among others, is that you can apply not just enclose, but any function. So, that would pay off big time in the case where you're applying a simple function like tally, because it doesn't actually have to form each, form the array before applying the tally. It knows. It just needs to count. So, in this case, special code, here we come. Now, fret can also be trailing instead of leading. And to do that, you use the 2 cut and the -2 cut. So here, the fret is the trailing comma, and I'm applying enclose to each cut, so you have trailing commas. And then if you want to exclude the fret, exclude a comma in this case, then you use the -2 cut. Okay? And again, frets can be indicated by ones in a Boolean vector left argument to the derived function. So enclose each cut with the fret being the trailing one. So you get 1, 3, 1, 2, and then 3, 4, 5. And again, if you want to exclude the fret, use -2 instead of 2. So it excluded the fret in this case. Oh, and in the case of the 2 and the -2 cut, the the ones indicate the ends of the cuts rather than the beginnings. So now in an application of cut to process CSVs, X is Applemon data, as it happens, and it's CSVs. So the structure of the data is such that lines are terminated by carriage return line feet, and if within each line the values are separated by commas. Okay? So this translates pretty directly into a short line like this. First, I exclude the carriage returns. After you do that, then the data is, has a trailing, each line has a trailing line feet. And within each line, if you catenate a comma to the end of it, then the values are terminated by a comma. Okay, so this is the thing in the curly brace is the function operand that I'm applying to the outer cut, excluding the frets. And within each line, I append a comma, and then so that the fret is the trailing comma, and I'm applying enclose to each cut. So T is a matrix, and the first 4 lines look like that. So I showed this to Stefano in Milano, hoping to impress him, and he immediately pointed out that for some CSVs there are commas within quotes. So how do I handle that? Well, let's see, Notepad. Here we are. So we can handle that using the Boolean left argument that we can supply to cut. So the real commas, the commas that are not within quotes, it's a standard computation. You find the commas and they're not within quotes, and then you append a 1 to the end of it, because here you're appending a comma. So it's the same outer structure, but inside you're using the Boolean vector to indicate the frets. And then again you're enclosing each cut. So with a Boolean vector left argument, you can have arbitrarily complicated indications of where the cuts, where the frets are. The 3 and the -3 cut effect tessellation, and a tessellation is just a moving window in the data, but in all dimensions, because the data can be an array of any rank. And the left argument to the derived function is a 2-row matrix. The second row indicates the size of the window, and they can be different in each dimension. And the first row of the matrix indicates the amount of movement. In this case, I'm moving 1 at each step. And again, the amount of movement can be different in each dimension. So here I have a 3 by 3 tessellation, moving 1 step at a time in each. And the difference between the 3 cut and the -3 cut is that in the 3 cut I include shards that are less than the full size. And if you want to exclude the shards, you can use a -3 cut. Some people have accused us of providing a game of life operator. So the next operator is under, first defined by Ken Iverson in 1978. Now I promised I would tell a joke, so here it is. If functions modify their data and operators modify their arguments, what modifies operators? Answer, Ken Iverson. So under is a dyadic operator, and Ken proposed this del diaresis symbol. It's a dyadic operator with two function operand, or operands. So first you apply the function g to the argument or arguments, and then you apply f to the result or results, and finally you apply the function, the inverse of g to the result of f. Okay? The idea is that the function g transforms the arguments into easier domain, or where f is an easier function. So, and then you apply f, and then you apply the inverse of g to get the result back into the original domain. It's under is commonly called dual in conventional mathematical notation, but the fact that we have specified it as a dyadic operator makes it clear that the duality is with respect to a function g. So when mathematicians talk about dual, they often just say dual this, dual that, but they don't tell you that there's a function g which may differ from context to context. So example, a simple example. Multiplication is plus under logarithm. So some of you may know what a slide rule is. It's also the basis of why logarithms are useful. An example from real life, under anesthetics. So first you apply anesthetics, and then you do the operation in a less painful domain, and hopefully you apply the inverse function. So once you're attuned to it, you can find examples of under everywhere. Like, how do you prepare dinner? You open the fridge, take the food out, and then you apply the inverse function, which is to close the fridge, and so on and so on. You can, once you're attuned to it, you can find it everywhere. Finally, a non-trivial example for doing digital multiplication, which is the same as polynomial multiplication and convolution. So if you do this multiplication using the so-called Scholes method, it's an outer product, so it's very inefficient if you get, like, say, 10,000 digits or 100,000 digits or millions of digits. But here's a specification for a fast digital multiplication. First you apply the fast Fourier transform, which is an n log n procedure. Then you apply multiplication, This is the ordinary vector multiplication in APL. And then you apply the inverse Fourier transform. Again, I encourage you to download the discussion papers and try it out. There are models in the papers, and give us feedback. Thank you.